You are watching an NBISD TV, Channel 19 production.
Hey, welcome to another edition of That Geometry Show. I'm your host, Kevin Corpy, and today we're going to be talking all about angles. We're going to talk about angle measure, angle comparisons, angle this and angle that. So I hope you're ready to get funky. We got a lot to do today, just like usual, about 40 minutes worth of material that we've got to cram inside of 30 minutes of time. So let's just jump right in. All right, today, lesson 3, we're going to be talking about angles, exploration, and relationships. This is going to follow along with your Glencoe Geometry textbook, chapter 1.6 and 1.7. Now, it's always good to know in advance what we're going to be talking about today. So by the end of this lesson, you should be able to, number 1, identify angles and classify angles. Number 2, you should be able to use the angle addition postulate to find the measure of angles. Number 3, you should be identify and use congruent angles and the bisector of an angle. Number 4, you should be able to identify and use special pairs of angles. And number 5, you should be able to identify your favorite math television program host. Yeah, that's me. All right. Now, remember from lesson 1 that a ray has one fixed end and extends indefinitely in one direction. For example, down here in this diagram, ray YV extends indefinitely in this direction. Now, ray YZ will start at Y, but it goes in the opposite direction. Okay, these two rays are basically pointing in opposite directions, but they share a vertex. So they're not the same ray. We call them opposite rays. A pretty fitting name. Okay, they do share a common endpoint, but they point in different directions. And opposite rays are always collinear, which means they are on the exact same line. Now, an angle is usually formed by two non-collinear rays, meaning they're not on the same line, with a common endpoint. The common endpoint is then called the vertex of the angle. Now, if you look at this angle down here, I've given you an example. I have ray QS and ray QR. The angle is formed by the distance between the two rays. Now, naming angles is a very important thing. Let's talk about how we can name it. We have 3 points. Q is the vertex, R is some point on one ray, and S is another point on the other ray. We can name the angle by always putting an angle symbol like this in front of the name. So we're going to read this as angle Q. We can just use the vertex in this case and call it angle Q. We can also use a 3-point notation. If we do that, we're going to start with one of the points on the rays. The vertex is always in the middle, and then the other point is at the end. So we can call this angle RQS, or equivalently, angle SQR. What we cannot do is call this angle RS. That is a big no-no. We can't just use the 2 points. We have to have 3 points or 1 point. And similarly, we cannot call this angle SR. And if you don't believe me, just ask Coach Fair. He'll tell you all about it. Now, there's one other way we can name this angle in this diagram here. Notice that there's the number 3 written in here. If there's a number written inside the angle, we can actually refer to it as angle 3. Okay? There you go. That's naming angles. We got 1, 2, 3, 4 different equivalent names for the exact same angle. Now, in the last diagram, there was only one angle. We have to be very careful when we're naming different angles that share a common vertex. If you look in the diagram below here, I have vertex B, but I have angle ABC and CBD and DBE. So if I'm trying to name this angle, I can't just say angle B. There's inherent confusion now. Which angle am I talking about? Am I talking about this one, or this one? So when there's more than one ray, or more than 2 rays actually, stemming from a vertex, we have to be more specific. So this would be a poor name to name any angle in this case. So what are some of the names? Well, I have angle ABC. That's this one here. And of course, I can call that angle CBA. Those are the same angle. I have another angle here that has B as a vertex. That's angle CBD. And equivalently, that's angle DBC. So those are equivalent names for the same angle. And then I have this angle here, angle DBE. angle DBE, and that's equivalent to angle EBD, or angle EBITDA. All right. Now, that might appear to be all the angles that you see here, but look at this. Angle ABE. Angle ABE, which is the same as angle EBA, this is an actual angle here. And notice that it's formed by two opposite rays. If you have an angle that's formed by two opposite rays, we call this a, what do we call it? A straight angle. Yeah, I thought I heard it out there. And it makes sense because it's a straight line. We'll talk about that more later on, what the angle measure is. Okay? And again, it's a straight angle because the two rays forming it that share vertex B are opposite rays. Okay. Now, whenever we have an angle is going to separate the two-dimensional plane, the flat plane, into three distinct parts. If you look at this diagram over here, we have angle WXY. We have basically something that's inside the angle called the interior of the angle, and an example would be point A. Remember, we name points with just a single capital letter. We say point A is on the interior or inside the angle. We also have the exterior of the angle, and if you notice over here, point B appears to be on the outside or the exterior of the angle. And we also have the angle itself. Okay, so in this case, the angle itself is, we can call it angle X because there's no confusion here, or we can call it angle WXY. Okay, so three different parts that the plane is divided into with any given angle. Now, once we have angles and we know how to describe their names, we're interested really in measuring angles. Now, we typically measure angles in a unit called degrees, much like temperature. Okay, and we measure in degrees using this fancy diagram down here, which is actually a physical device called a protractor. Ask your teacher if you haven't seen one before. I'm sure she's got plenty laying around. You might get a chance to actually use one. Now, let me show you how to use one. Let's say we have this angle right here, which I'm going to zoom in on. Okay? We've got an angle that's formed by point A, point B, and point C. To measure this angle right here, which is the measure of angle ABC, whenever we're measuring angles, we have to put a little m in front, meaning the measure. What we do is we line up the vertex at the center of the protractor, and we let one of the rays be flat along the bottom, running into the zero. Now, since I have it oriented this way, I'm going to use the inside scale. And all I do is I follow the numbers up until they intersect. So if you can see, it appears that I'm passing through 60. So this angle measure is approximately 60 degrees. And I say approximately because what if it was 60.02 or 61 degrees? Sometimes it's very, very difficult to get a real accurate reading from a physical device because there's error in the way we read it, and there could be error in the actual device itself. But it does give us a good idea of what the angle measure is. Now, just to extend it, what if I had another point over here, point D? Now I can actually measure this other angle, which is angle DBA. The measure, then, of angle DBA, I would have to now use the outside because I'm orienting it this way. The outside starts at 0 down here. So if I follow along the outside here, I'm going to get an angle measure that lines up with 120. So the measure of angle DBA is 120. Now we're measuring these things in degrees, and degrees do have a unit of measure here, a symbol that we write. I could write 120 with a little bubble at the top, like we do for temperature. But every angle that we're going to be measuring this year is going to be in degrees. So it's okay in this context if we go ahead and leave the little degree symbol off. Your teacher and everybody else who's going to be looking at your work will understand that you're talking about degrees. That's not necessarily the case as we climb up the ladder in mathematics, where there's a different way to measure angles. But in geometry, you should be safe. I would say that it would be a good habit to get into putting it every single time, though. Okay, let's move right along there. We got more postulates. Okay, we have more postulates here. The first one we're looking at is called the angle addition postulate. And remember, a postulate is one of those no-duh statements. Okay? Here's what it says. Notice I have two different angles here, angle 1 and angle 2. I can call the entire angle, angle HIK. And it's composed of two smaller angles, angle HIJ and angle JIK. Basically what the postulate says, if I take the measure of HIJ and add it to the measure of JIK, I should get the measure of the entire angle, angle HIK. Right? Well, really, that's kind of a no-dust statement. Let's put it to work here. What is the measure of HIJ? I'm going to identify it as this angle. If the measure of JIK, we know this one is 45. Sometimes it helps to label a diagram. I'm going to put it there. And HIK, the entire angle, is 100 degrees. So I'm trying to find the other smaller of the two angles. I'm going to call that question mark for now. Well, let's go ahead and use the postulate. I know that the question mark, which is the measure of angle HIJ plus the measure of angle JIK, is equal to the measure of angle HIK. And I'll just fill in what I know. The measure of angle HIJ, well, that's what it's asking. So I'm just going to leave it as that, plus the measure of JIK, that was given as 45 degrees, and that equals the entire measure, which is 100 degrees. So this is really algebra, but instead of calling this x, we're just going to keep it as our unknown quantity. I subtract 45 from each side, and I get the measure of angle HIJ is 100 degrees minus 45 degrees, which is, of course, 55 degrees. And there you go. And it's a good habit to get into checking. If I take 55 plus 45, what do I get? Well, I get 100, and that's the length of the whole, or the measure of the whole thing. So we know we're right. Okay, so moving on now to classifying angles. We can classify angles by their relative size to 90 degrees, okay? Some of y'all are probably familiar already with something known as a right angle. A right angle is basically an angle that measures 90 degrees. And whenever it measures 90 degrees, it's typical to put this little square to denote the angle measure instead of an arc. Now, a square is good because a square has 4 right angles inside of it. Now, a right angle is basically, if we're trying to build something that's strong and plumb and square, we want all our angles to be right angles. So a right angle is a 90-degree angle. Now, in relation to 90 degrees, we can have an angle that measures smaller than 90 degrees or less than 90 degrees, and these are called acute angles. So any angle smaller than 90. For example, right here we have a 54-degree angle. That's an acute angle. Some other acute angles could be 23, 21, 57, anything smaller than 90. Okay? Now, if we look at an angle that is larger than 90 degrees, beyond a right angle, we call those obtuse angles. Okay? So anything greater than 90, but less than 180, we're going to say, is going to be an obtuse angle. So, example, 130 degrees, 150 degrees, 91 degrees. Okay? Anything greater than 90. Now, in geometry, we're not going to typically look at angles that are larger than 180, which brings us to something called the straight angle. If you remember what I talked about earlier about a vertex with opposite rays, or an angle formed by 2 opposite rays, we called it a straight angle. This is a straight angle, and the degree measure of a straight angle always equals 180 degrees. Okay? So we have one angle that equals 90, one less than 90, one greater than 90, but less than 180, and of course the one that's 180. And we won't look at anything in geometry this year that's bigger than 180. Okay? Now, it's time for another definition. Blank angles have the same measure. Well, we talked about this term also when we had segments. Segments that had the same measure were called congruent segments. So angles that have the same measure are again called congruent angles. Now, which of the angles above that we classified are congruent to all others in the same class? Well, are all right angles congruent to each other? Another way to phrase that is, are all right angles equal to 90 degrees? And the answer is yes. Because they all equal 90 degrees, all right angles are congruent to all other right angles. What about acute angles? Are all acute angles congruent to all other acute angles? Well, not necessarily. And in math, if it's not necessarily true or not always true, we say it's false. For instance, I can give you a 54-degree angle, which is acute, and I can give you a 60-degree angle, which is also acute. They're not the same measure, so not all acute angles are congruent. Same argument with obtuse. I can give you 2 angles greater than 90, like 130 and 131. They're not congruent. Now, what about straight angles? Since straight angles equal 180, every straight angle is also congruent to any other straight angle. So basically, if you look above, the ones that had equals for their measure are the ones that are congruent to all the others in the same class. Now, back kind of to the straight angle here and the right angle. If we have two angles that add up to 180, two separate angles, not a single angle, then we say that those two angles are said to be supplementary. Supplementary angles, or they are supplements of each other. Two angles that add up to 90 degrees are said to be complementary angles, or we say that the two angles are complements of each other. Okay, another definition here. An angle blank is a ray that divides an angle into two congruent angles. Well, that word is a bisector. An angle bisector is a ray that divides an angle into two congruent angles. Okay, let's look at those three definitions and see if we can't get a better idea of how we're going to be using them. Here's an example. We have a diagram that has many angles, lots of rays coming out of a common vertex or a common point called G. Now, if ray GD bisects angle CGE, let's identify where that is. Ray GD is right here. Okay? It bisects angle CGE. Notice we need the three-point definition here, or we're not going to know what angle G is. So we're talking about this one. So if this ray bisects this angle, we're now asked which angle is congruent or has the same measure as angle CGD. Well, which one is CGD? That's this one here, CGD. So I'll show that in red. Well, if we look at the definition, a bisector divides an angle into two congruent angles. So if this is the bisector of this larger angle, then we know that angle EGD, or equivalently angle DGE, has to be congruent. And if two angles are congruent, we typically put the same little arc between the two, showing that they are the exact same size. Okay? Now another question. What other angle is congruent to angle CGE? Well, let's look. CGE is our original angle right here. How are we going to answer that? Well, looking at the diagram, we can see that FGC, angle FGC, is a straight angle, which means it equals what? 180 degrees. Now notice this little symbol here. It's kind of hard to see, but that means that angle FGE right here is a right angle, and a right angle always measures 90 degrees. So here we go. Just by a little reasoning, if this is 90 degrees and this angle here is 180, kind of by the angle addition postulate, we know that angle EGC or angle CGE, the same thing, is congruent to, and we can use the congruent, to angle FGE. They are both right angles. They're both 90 degrees, and they add up to 180, which makes the straight angle. Let's take a break now and watch a few good public service announcements, and we'll be right here when you get back.
This is a wonderful resource for the district, for the students to come to and the parents to come to, because I can answer those questions on where to start and you know, what's the first step you need to take in order to make college a reality. There's a lot of resources in here. There's a lot of printed material, and of course we have 16 computers, and I recommend don't ever pay anybody to pay for a scholarship search, because those are things that we can do for free, and I can show you how. I had a senior who was not sure that she was ever going to make it to college, and she got into UTSA. I'm so proud of her. She's very successful. I just heard from her recently. She got a very large chunk of financial aid through her research efforts. Come visit us. We're here. We want the word to get out to the community that this is a resource that NBISD provides for our students, and take advantage of it. It's free.
My name's Lisa, and in 9 years I'll be an alcoholic.
Hi, Lisa.
I'll start drinking in 8th grade. And I'll do some things I don't really want to do. So by the time my parents talk to me about it, alcohol won't be my only problem.
Kids who drink before age 15 are 5 times more likely to have alcohol problems when they're adults. So start talking before they start drinking.
My parents won't believe it could happen to me.
Welcome back to That Geometry Show. I'm Kevin Corpy. If you're just tuning in, remember that every document that I'm using that you're seeing there at home is available to download on our district's website at www.newbraunfels.txed.net. Let's jump right back into angles. When two lines intersect, they form 4 angles. When they intersect to form 4 right angles, we say the lines are I almost heard it out there. It's perpendicular, okay? Kind of a long word. They're perpendicular to each other, and we denote it by this symbol here. It's kind of an upside-down T, but it kind of gives the impression that we have a vertical and horizontal. Now, not all lines are perpendicular. Let's look at these 2 lines here. They intersect. Now, it's very difficult to tell from the diagram which ones, what the measure is, okay? So unless you have markings on here that tell you what the sizes are, you can't assume that they are any type of size. But we can talk about relations among these 2 angles, okay? If they intersect, it's useful to classify angles by their relationship to each other. So the first one we're going to look at is adjacent angles. Adjacent angles have a common vertex and a common side with no common interior points. So let's look at that. Here's a vertex. If they share a common side, which 2 angles share this side? Well, angle 1 shares this side and this vertex with angle 2. So angles 1 and 2 are adjacent. Similarly, angles 2 and 3 share a common side. They're adjacent. Angles 3 and 4 are adjacent, and angles 4 and 1 are adjacent. Adjacent basically means next to. Now, can an angle be adjacent to itself? Well, let's see. If I'm looking at angle 1, it actually has 2 rays in common, which definitely satisfies the condition of needing 1. But this little part right here, they can't have any points on the interior that are the same. And of course, if it was an angle adjacent to itself, all the points would be common. So no, an angle cannot be adjacent to itself. The other type of angles that we're going to be looking at are called vertical angles. Vertical angles are non-adjacent angles. They're not next door to each other. They're actually across from each other. And here's the nice thing about vertical angles. Vertical angles are always congruent to each other. Now, which angles here are vertical? If you look at the diagram, 1 and 3 are directly across from each other, and you can actually circle them with a vertical oval there. So angle 1 and angle 3 are vertical angles. Now, of course, I can turn my paper sideways, and I can do the same little vertical trick. 2 and 4 are directly across from each other, and even though they're horizontal in this case, we do call them vertical angles, and they're also congruent. So basically, angles 1 and 3 are vertical and they're congruent. Angles 2 and 4 are across from each other. They're vertical angles, and they're congruent. Now, one last definition, a linear pair. A linear pair are adjacent angles formed by opposite rays. Linear pairs will always be supplements of each other. Now, which angle above are linear pairs? Well, let's see. What do we have? Linear pairs are formed by opposite rays. We've seen this earlier in the program. Angle 1 and angle 2 form a linear pair. So we've got angle 1 and angle 2 form a linear pair. Angle 2 and angle 3. Where have I seen these guys before? They form a linear pair. Angle 3 and angle 4. Wow, these appear just to be all the adjacent angles. And in this case, they are. Angle 4 and angle 1. They're adjacent, and in this case, they also form a linear pair. Now, that's not always the case. Not all adjacent angles form a linear pair. But in this example above, they certainly do. All right, we're getting close here. Let's look at this example. If the measure of angle MYZ is 160, what is the measure of MYW? Ooh, let's see. MYZ is 160. MYW is the one we're looking for, so that's this one here. How are we going to find that? Well, I know by the angle addition postulate that 4x plus 2x plus 10, that's the measure of angle WYZ, those have to add up to be the entire angle MYW, which is 160. So by using the angle addition postulate, I've set up this little algebraic equation. 4x plus 2x plus 10 has to equal the total angle, which is this. So now I just do algebra. 6x plus 10 equals 160. 6x then has to equal 150. And dividing both sides by 6, I get x equals 150 divided by 6, which is 25. Now again, we might feel a sense of accomplishment finding x, but have we really answered the question? No. What is the measure of MYW? So MYW, the measure of angle MYW, is equal to 4x. So I now have to take the value of x that I found and plug it in. So it's equal to 4 times 25, which 4 quarters makes $1. So it has a measure of 100 degrees. So make sure you answer the question. All right, we're almost done here. It's almost time for the say what. One more example. Name two angles that are adjacent to angle MTV, or WTV, sorry, WTV. Two angles that are adjacent. Remember, adjacent angles have to share a side and a vertex, but no common interior points. So it appears that angle 1 right here is adjacent to this angle, and adjacent to it also is angle 3. So 1 and 3 appear to be adjacent to each other. Now notice some of the other answer choices. Angle 1 and angle 2. Well, those are adjacent to each other, but 2 is not adjacent to the one that we want, so it's not the choice. Angles 2 and 3, same argument. They're adjacent to each other, but not to the one we want. Well, angle WTV and 3, remember what I said earlier about an angle cannot be adjacent to itself, so that's not the answer choice. Okay? Now it's time to do our little segment we call Say What? Okay. We're going to circle the right answer. We're going to keep this short and sweet today. Circle the right answer. Angles are measured in units called sides or degrees. Well, we measure them in degrees. Okay? In figure 1 below, down here, angle 2 and angle 3, which are next to each other, forming a linear pair, are complementary or supplementary. Remember, complementary adds to 90, supplementary adds to 180. And since they form a linear pair, a line adds up to 180. They've got to be supplementary. Number 3, a compass or a protractor is used to find the measure of an angle. I haven't even said the word compass today. A protractor is the tool used to measure angles. In figure 2 below, the two angles shown are, let's see, one of them is 120 and the other one's 120. Can they be supplementary? Do those add up to 180? No, they add to 240. Are they congruent? Why, yes. They have the exact same measure. So they are congruent. Number 5, in figure 3, this one right here, angles 5 and angle 6 are they vertical? Are they across from each other? No, they're next to each other, so they have to be adjacent. Okay? Number 6, perpendicular lines intersect to form what type of angles? Obtuse, that means greater than 90, or right angles. Well, remember the symbol for perpendicular is actually a symbol that has two right angles. So perpendicular lines intersect to form right angles. Number 7, in figure 3, A is called the side or the vertex of angle 6. Well, remember, it's the common point for the two rays, and we call that the vertex. Number 8, in figure 1, back over here, angles 1 and 4 form a what? A linear pair or a right angle? Well, they do form a line, so it's got to be a linear pair. And finally, in figure 4, the last one down here, ray KM is the blank of JKL. Well, it divides it into two equal angles of 53 apiece. Those are congruent, so that must be the angle bisector. Well, that concludes today's lesson on angles. I hope you all had fun out there, and I want to thank you all for tuning in. Join me next time for another exciting episode of That Geometry Show. Until then, I'm Kevin Corpy, and I'll catch you on the flip side.